Each of them are their own auctioneers. You can have a bunch of auctioneers yelling at each other.
Okay. So, let's start making things really interesting. We'll focus on Einstein's solid, like we've just been working on. But we've pretty much done everything interesting there is to do with one Einstein solid. We've listed a table where we were listing microstates, and then we figured out how to calculate the multiplicity of a macrostate, right? There's not much more to say about a single solid. So what we're going to do now is we're going to let two Einstein solids interact with each other and exchange energy back and forth. And that turns out to be enough to introduce a whole new idea of physics. All right. So, next big section. We will have to introduce one fundamental assumption. You cannot prove this assumption. You can only say it seems reasonable, assume it, calculate all the consequences of that, and then go into the lab and check them. Okay? So, we're going to introduce the fundamental assumption of statistical mechanics, and there will be a glimpse at the second law of thermodynamics. Okay? Alright, so all we're going to do, like I said, is go up kind of one more notch up in complexity. We'll take two Einstein solids. We will surround them in a completely insulating container so that none of the rest of the universe can affect them. And just let them exchange, and we'll make it a slow exchange of energy back and forth. Okay? Alright, so the scenario is two Einstein solids weakly, W-E-A-K-L-Y, weakly interacting with each other and isolated from everything else. So here's my drawing. First of all, I'll have some kind of really good insulating box, thermally insulating box. Okay, that's where we're going to put the solids in. I will represent the solids just as two chunks of matter. Okay, here's solid A. Here's solid B. Let's say solid A has capital N sub A oscillators. That number is not going to change. The number of oscillators in solid A is not going to change. Solid B has capital N sub B oscillators. That number also is not going to change. But I will allow them to slowly exchange energy back and forth. Okay? So this represents energy exchange. I can, because the energy exchange is slow, I can, at any given time, talk about how much energy each one has. Okay? It's changing, right? The amount of energy this one has, because it's exchanging with this one. The amount of energy this one has is going to change with time. Same for that one. The amount of energy this one has is going to change with time. But these changes aren't going to be happening suddenly. It's going to be a gradual process. So at any given time, I can ask, how much energy does this solid have? How much energy does this solid have? since I'm talking about energy in the form of lattice vibrations, the energy will always be some quantum number times h times f. Okay? So I'm going to also say, at any given time, that solid A has Q sub A quanta of energy, and solid B has Q sub B quanta of energy. So note, the total energy of solid A will be Q sub A times H times F, and the total energy of solid B will be Q sub B times H times F. But now, because all I have inside here are the two solids slowly exchanging energy back and forth between each other, but isolated from everything else in the universe, I know one thing has to be true. The total energy of the two together cannot change. Because that could only come from something else, and there is nothing else. Okay? So I do have a very important constraint. U total, the total energy, which is the sum of the energies of each solid, UA plus UB, is fixed. Okay? That's very important for this scenario. Note that that's equivalent to, so I can also talk about the total number of energy quanta, Q total, which will be the number of quanta in solid A, Q sub A, plus the number of quanta in solid B, Q sub B. That total of the energy quanta is also fixed. Question?
Is that equivalent to saying it's a closed system?
That is what? Yes, it's a closed system. Yes. Isolated means closed. Okay? Okay, so all I want to know is what's going to happen. Okay. As I let them sit there over time, what are they going to end up in? What kind of configuration? How much energy in each one? That kind of thing. Okay? Nothing's going to happen quickly, but and so I may have to wait a while. I may go off to lunch and come back, but after I've waited a long enough time, I will discover that these energies, remember UA and UB were slowly changing. Eventually they don't ever change anymore at all. We've reached equilibrium, thermal equilibrium. I want to know what that's going to look like. How many energy quanta, for example, in each. All right, so let's start with some specific, simple versions of this scenario. Okay? So we're going to start simple. I'm going to take very simple and small numbers. Let's take each solid to have an equal number of oscillators. Let's take it to be 6. Each solid has 6 oscillators. You might say that means we have a total of 12 oscillators. You could say that if you want. But each one has 6, equal number. Okay? And just to make the numbers simple, let's say that the total energy quanta, QA plus QB, Q total, because that's the thing that's fixed, is 12. Okay? I just happened to pick, so if the numbers were nice, a total number of energy quanta equal to the total number of oscillators. You don't have to, you're not limited to that. I just picked it so that the numbers would be simple. Okay? All right, now remember what we mean by a microstate. Well, for one solid, we meant for a microstate that you tell me in detail how many quanta each oscillator in that solid has. Okay? Well, now I have 2 solids. So now a microstate means to go down the line for all of these oscillators, there are NA of them, happens to be 6, and down the line for all these oscillators, NB of them, also happens to be 6, and one by one ask them how many quanta they have. That'd be a microstate. Okay? All right, so a microstate of this two-solid system is a detailed partitioning of Q total quanta over Na plus Nb oscillators. I'm not even going to make such a table by hand, right? Because there would be 12 entries. I would have to tell you how many quanta each one of the 12 oscillators has for a given value of Q total. Okay? Not even going to go there. Not even with just 6 and 6 oscillators. Okay? Now what do I mean by a macro state in this two-solid system? I mean where all we specify now, we specify the total energy of A. All you got to do to specify that is tell me how many quanta total solid A has, and the total energy of B. And all you got to do to specify that is tell me how many quanta solid B has, Q sub B. Of course, I have to always remember the constraint that QA plus QB is fixed at some total Q total. In my simple example, Q total is 12. Okay, like I said, I'm not even going to try to make a table by hand of listing all those microstates. And that's just 6 and 6 oscillators. Instead, I'm going to go to Excel. Okay? And I'm not even going to list all the microstates. Because even with just 6 and 6 oscillators, the number of microstates grows rapidly. So I'm going to show you how I'm going to kind of do the bookkeeping. And you're going to end up making a similar kind of spreadsheet in one of the homework problems. Probably more than one, in fact. And by the way, now I want you to be able to construct this kind of a spreadsheet I'm going to show you yourself. But in order to give you some guidance, what I did is I saved basically the image of the spreadsheet contents as a PDF. That way you can see what it looks like without clicking on a cell and seeing what the command was. Okay? And I have uploaded that into the content on Blackboard. So you can see this picture on Blackboard. Now, because this is a live Excel spreadsheet, I can click on the cells and you'll be able to see the commands I entered. Okay? All right, so how am I organizing this? We just need some way to organize what's going on. Really, all I'm going to be interested in is listing the macro states. So how am I going to do it? Well, first of all, I just listed here 6 oscillators in solid A, 6 oscillators in solid B. Okay? All right. Now, this is important. Let's work our way down this first column. It's labeled by the possible values that QA could be. Remember, I have a total in this application. I just assumed a total number of oscillators of 12. Okay? And one way to describe the macro state is to tell you what QA is. Right? Because once I tell you QA, you can figure out what QB is. So I could just say I'm specifying a macro state by telling you what QA is. Well, if Q total is 12, I know how many distinct values of QA you could have. Anything from 0 up to 12. So oscillator A could have none of the quanta, it could have one energy quantum, all the way up to all 12. And for each column of QA, it's easy to make a corresponding column for QB. Because I know the total Q is 12. once I specify a value for QA, QB is just 12 minus that. So far, yes? So this is just a way to count and label the macro states. I'm not even going to try to draw the micro states. Okay? Now, here's a really important column. For any particular value of QA and NA, I can use my multiplicity equation for the Einstein solid to calculate the multiplicity, omega, for solid A. And the way I would do that, right, the multiplicity for solid A, when it has N sub A oscillators and Q sub A quanta, is just that equation 1 we just saw before the break. QA plus NA minus 1 factorial over QA factorial times NA minus 1 factorial. Okay? So you could go down this second column, and for each value of QA, NA is fixed at 6. You can use that formula, right? And calculate the multiplicity of just solid A given that number of quanta. Everybody understand where these numbers came from? You're going to have to do a similar kind of thing. So now's the time to ask if you don't understand how I'm getting the numbers you see in this column. Notice there are 6,188 detailed ways to partition 12 energy units in amongst the 6 oscillators in solid A. Right? That's what this number right here means. Of course, you can do a similar thing for solid B, yes? For its value of QB. You understand what I'm saying so far? So you'd have a similar equation for calculating the multiplicity for solid B with NB oscillators and QB energy quanta. That's QB plus NB minus 1 factorial over QB factorial NB minus 1 factorial. And that's how I get this column. Multiplicity of solid B. Okay, now those are the individual solids. What I really want to know is the total multiplicity of the compound system for each one of these 13 macro states. Because the compound system is 2 solids together. Right? So, the total multiplicity of a macro state, the macro state is specified by telling you QA, and by default then you also tell me QB, of the system A plus B, the 2 solids together. I will denote that omega sub AB. Okay? The answer is, don't overthink it. It's just the multiplicity that solid A had times the multiplicity that solid B had. Because, let's take this line right here, line 7 in the spreadsheet. That's the macro state with QA equal to 1, and therefore it must be true that QB is 11. There are 6 microstates of solid A for this QA of 2. There are 4,368 microstates of solid B with the QB of 11. But for every one of these 6 microstates in A, there are 4,368 microstates in B. So the total multiplicity for the 2 solids together, for the macro state of 1 and 11, is 6 times 4,368, which is 26,208. Okay? So then I made another column working all the way down, which is the product omega A times omega B. And an amazing thing happens. because the omega A's are growing as you go down, because the QA is growing, but the omega B's are decreasing as you go down, because the QB's are decreasing, the product grows, peaks, and then decreases again. Okay? So there is a particular macrostate that has the largest multiplicity. And it happens for this particular configuration of solids to be this one, where the energy quanta are shared equally. Okay? All right, so next thing I want to write. Okay? How many microstates total are there available to this two-solid system? Okay? That's the next thing I want to ask. How many total microstates are available to A plus B? One way to find that, I'll call that capital N micro, the total number of microstates. One way to do that, let me just show you from the spreadsheet. All you got to do is take this column, column E, which is, this is the total multiplicity of A and B together for the particular macrostate 012. And then work your way down. So you got 6,188 microstates there. Then if you went to the macrostate 111, you have 26,208. That's the multiplicity, so that's the number of microstates there are. Do you see what I'm going to do? I'm just going to go down this column and add them all up. I'm just going to sum the multiplicities in that column, because each one of those is the number of microstates available. So the sum of that column, that's this number at the bottom, is the total number of microstates available to this two-solid system. Okay? So all I got to do is sum the total multiplicity in any given row, that's the omega AB, for QA going from 0 to Q total. And that is exactly what I did in column E in the spreadsheet. And you can see I got 1,352,078. Okay? Now here's another way you could get that total number of microstates. You could say, well, it's really just, I can think of this as really just one big solid with Na plus Nb oscillators and Qa plus Qb quanta. How many ways, how many microstates are there? Use my equation 1 for that. Okay? So another way to do it is to say, well, I'll just use the counting equation, omega, equation 1, for Na plus Nb oscillators and Qa plus Qb quanta. Total, because for the two solids together. Let's remember that in our case, Na plus Nb is 12, and Qa plus Qb is 12. So this is the number way. Remember the formula is Q plus N minus 1 factorial. Right? I'll write it all out. Q total plus N total minus 1 factorial over Q total factorial times N total minus 1 factorial. So let's see what that is for our simple two Einstein solid system. So Q total is 12. N total is 12. 12 plus 12 is 24. 24 minus 1 is 23. So the numerator is 23 factorial. The denominator, I have Q total factorial. 12 factorial. And N total minus 1 factorial. 11 factorial. Now you check that on your calculator or on Mathematica. Okay? And you will discover that that number is 1,352,078. It's a lot. It's a lot of microstates. Now you see why I don't want to make a table by hand of all those microstates. Over 1 million of them. Okay? And this is just with a measly 6 and 6 oscillators. Not even close yet to what a real solid would be. Right? Not even close to what a real solid would be. Okay? But here comes a really important point. All right? You ready? Assumption. All of these, draw an arrow over to here, all of these microstates are equally probable. Exclamation mark. Okay? All of these microstates, the 1,352,078 microstates, there's nothing that makes any one of those any more special or less special than any of the others. And they are all equally likely. That's assuming that we have come to what's called thermal equilibrium. Okay? Okay, so that is in fact the fundamental assumption of statistical mechanics. So now we're going to write that down. So we'll put say a star like this. The fundamental assumption of statistical mechanics. In an isolated system, well, remember our two solids were in an insulating box, right? That isolated them from the rest of the universe. In an isolated system, in thermal equilibrium. So, when we first put the solids in the box, we may have to wait a while, let them slowly exchange energy back and forth until there's no more clear trend of energy going one way or the other. Settle down until, so that the energies of each isn't changing. They've settled into some configuration. Then you know they're in thermal equilibrium. When you're in that situation, all accessible microstates are equally probable. All accessible microstates are equally probable. Accessible here refers to whatever constraints you're limited by. I'm limited by, in this series of columns in the spreadsheet, the constraint that QA plus QB, Q total, is 12. So no microstate that deviates, no microstate with a Q total of 13 gets to get counted in here. Because that's not the condition I have. My Q total is 12. So a microstate with a Q total of 13 isn't accessible to this system. But those 1,352,078 microstates with a Q total of 12, they are accessible and they're all equally probable. Okay? All right, if we accept that as true, then there are some things we can conclude. Okay, so here comes some comments. Bullet. If all, again, microstates are equally probable, then macrostates, macro, we've got to be clear what words micro and macro, then microstates with larger multiplicity are more likely. Understand what I'm saying? If they're all if all the microstates are equally likely, then just go to various rows here. The rows are representing macro states. Find a row that has a larger total multiplicity, omega A times omega B, up like right about here. This particular macro state with 6 and 6 has 213,444 of these microstates corresponding to it. Well, that's a lot more than, say, this macrostate up here, which has only 6,188 of the microstates available to it. So just from simple counting, this macrostate is going to be more likely observed than that one. Okay? If you imagine the system is spending time equally amongst all of them, then you're more likely to find it in this one when you look than that one. Now, in this toy model, there will still be sometimes you'll find it in this state. But you're more likely to find it in this one. Or maybe that one and that one. Right? Than that one. Okay? It's just from counting. It's sheer probabilities. Okay? Okay. So, we saw, right, for this system, that the macro state with the largest multiplicity happened to be equal sharing of the energy. It's because I have equal number of oscillators. That might be different if I had different numbers of oscillators in the two. But in this case, I have equal sharing of the energy quanta. That has the largest multiplicity. I can, if I want, calculate a probability for each one of the macro states. It's not hard. Just take the multiplicity of that macro state, that's the number you see in these cells, divided by the total number of microstates. Okay? And then you can get these probabilities. So notice the macro state with 6 and 6 quanta, it has the largest probability, although 5 and 7 and 7 and 5 are not too much less likely, yes, than 6 and 6. But 0 and 12, or 12 and 0, are considerably less likely than, say, 6 and 6. So I made a plot. I made several plots. Here's a plot of the total multiplicity. That's the omega A times omega B vertically versus QA horizontally. So QA goes from 0 to 12. It's nice and symmetric with the highest multiplicity at 6. Okay? Looks similar if I would plot probability of the macro state versus QA. And I did that, although I decided not to do that one as a bar chart, but just to do it as a kind of a line graph. And that's this. Okay? Again, the highest probability, which is just a little bit under 0.16, is for QA equal to 6. Okay, fine. But that is two solids, each with 6 oscillators, i.e. 2 atoms each. Okay, if you want to call that a solid. We know we're going to have more atoms, and therefore more oscillators than that. Okay? So let's go up a little bit. Let's go to what I did next was back to this part of the spreadsheet, and now go up a little bit. And the next thing I did was solid A, 100 oscillators. Solid B, let's give it the same number, 100 oscillators. And just to keep the numbers simple, let's say Q total is also 100. Again, you don't necessarily have to have all those numbers the same. I'm just picking things to make them nice and simple. Okay? So I want to make the same kind of table as I did with 6 and 6 and 6. Okay? Now it's 100, 100, 100. And A and B, Q total. How many macrostates would there be? Macrostates will be delineated by the value of QA. So there will be 101. right? Because there are 101 possible values of QA. So I had that, it's easy to have Excel, just fill in the row, or the column, right? So the first column is the QA value, starting at 0 and going down to 100, okay? Then the next column, using this formula right here, is the multiplicity for solid A. With NA equal to 100, QA given by the value that you have as you work your way down this column. And now, look, the numbers grow, whew, pretty fast. Look, we're at 10 to the 23 with a QA of 22. Numbers are starting to get big, aren't they? For the multiplicity, multiplicity is growing fast. And I still only have 100 oscillators. That's 33 1/3 atoms. Right? And still not even close to how many there are in an actual solid. But let's see what we learned from this. Then I made the QB column. Obviously, once QA is specified, QB is specified. Remember, the total is, Q total is 100. So I made the QB column, and then I made the multiplicity for B. Look at the size of that number for QB of 100. And then I need the total multiplicity for the two solids together. That's the product omega A, omega B. And once again, I'm going to have a peak. Yes? Because omega A is an increasing function of QA, and omega B is a decreasing function of QA. And so the product is going to have a peak. And in fact, it looks like this. And the peak is indeed at QA of 50, where the solids share the energy quanta equally. And let's just see what that value is for the omega A, omega B at 50, 50. 50, 50. It's 1.8 times 10 to the 80. And of course, I can add up the omega total column, all those microstates, all in that column of omega A times omega B. That's the total number of microstates that are accessible to this two-solid system. 2.77 times 10 to the 81. And then I can make a probability column for each macrostate. Take that macrostate's total multiplicity, like right there, because that's the number of microstates for that macrostate, divided by the total number of microstates. And so again, QA and QB equal to 50, 50, 50, with the largest total multiplicity has the highest probability. Right? 0.065. With the ones nearby not that much smaller. Yes? But the extreme ones, the extreme macrostates, far away from the middle, at the tails, like 0 and 100, look at the probability of that. 10 to the minus 23. You're not going to find it in that state, in that macrostate. Right? You're not, the odds are so tiny that you might as well not worry about finding the system in that macrostate. And here's a plot of the probabilities, the macrostate probabilities for 100, 100, 100. And it peaks. Notice something, though, about this graph. This one for 100, 100, 100, and this one for 6, 6, and 12. I actually did that. I did 100 there. I probably could have done 200. Again, it won't make any big difference. Okay? Notice something? This peak is a narrower range over the horizontal axis, obviously, than this one. Okay? You can even be quantitative about it. If you want to quantify, say, the width of a peak, one of the things you do is called the full width at half max. All right? That means find the max of the peak, like for this one, it's just a little under 0.16. So half the max is a little under 0.08, and then find the width from here to here. That's the full width at half max. So I found that for that graph. I found the full width at half max for that graph. I estimated it to be about 6, whereas the full scale is 12. So the full width at half max is about half of the full scale, 50%. That's a way to measure how wide that peak is. Now do the same thing for this one. 100, 100, 100. Okay? The peak is about just a little under 0.065, so you go down to about roughly about here. I estimated, I'm just estimating here, I estimated how wide it was there in terms of horizontal axis. I got a value of about 14. Whereas the total width of this axis is 100. So this is about 14% of the total width, whereas that one was 50%. So my point is that my peak is clearly getting narrower. Okay? It's clearly getting narrower. All right. Let's make that a very explicit statement. As the size of the system increases, the macro state with the largest multiplicity becomes by far the most probable macro state. Now, let me just try to show you. For now, I'm just going to have to show you with kind of making a plausibility argument. I went from 6 and 6 and 12 with a pretty wide probability peak to 100, 100, 100 to much narrower. But this is still only tens of atoms. I expect an actual solid to have something of the order of 10 to the 23 atoms. Think about how much larger that is than even this case. Right, 10 to the 23 versus tens. Okay? It's so much larger your mind really can't even wrap around it, the idea of it. Okay? But maybe you can at least buy the following trend, the following statement. As the number of oscillators goes up and up, this peak gets narrower and narrower. Until, if you're at the type size of a typical solid, 10 to the 23 oscillators in each one of those solids, this peak is so narrow, okay, that if on this scale right here, which really, literally on this screen is about a meter, the width of the peak would be a picometer. Okay? Picometer. Bigger than a nucleus, right? But maybe a little smaller than an atom. That's how narrow the peak becomes. Okay? So that's what I mean when I say the macro state with the largest multiplicity becomes by far the most probable macro state. When the system's in thermal equilibrium, all you got to know is out of all that horizontal axis, which is listing all the macro states, where's the value, where's the macro state coordinate on the horizontal axis where the peak is? Because that's all that matters. Okay? That's where we're headed. I'm just kind of demonstrating it to you. Okay? Okay, now one other thing I'll state, and then we'll quit. Because the macro state with the largest multiplicity has so many more microstates than any other macro state, if you start out with the system not in the most probable macro state, it's going to evolve to that most probable macro state, and then you're not going to observe it to change from that. Just from sheer probabilities perspective. Not because it would violate any fundamental law of physics to be outside of that most probable macro state, but just from counting. That most probable macro state has so many more microstates available than any other macro state that just the odds are you'll never see it deviate from that most probable one. Okay? And that's what the second law is saying. Okay? So here's our first version. Our first version of the second law of thermodynamics. Okay? If a system of many particles, many to a physicist means 10 to the 23, Avogadro's number. If a system of many particles is permitted to change, I'll put in parentheses, while isolated from rest of universe, okay, there's the starting point. If a system of many particles is permitted to change while isolated from the rest of the universe, then the system will evolve to the macro state with the largest multiplicity and will subsequently remain in that macro state. Okay? And notice, it's just a statement about probabilities and having one state with an overwhelmingly large number more of microstates available to it than any other macro state. Okay? So if a system of many particles is permitted to change while isolated from the rest of the universe, then the system will evolve to the macro state with the largest multiplicity, and it will stay in that macro state. Okay? Yes?
So the isolated part, is that the assumption that all micro states are equally probable?
The assumption of equally probable microstates requires that the system be isolated.
Oh, okay, so that's that.
Yes. Okay, so we have stated the second law in one form. We're going to state other forms. Okay. All right, so on Thursday, we're going to start by working our way closer to dealing with situations where there aren't 100 objects, but more like Avogadro's number. Now that might seem like that's hopeless. 10 to the 23. It's huge. What are you going to do with that? Amazingly, it turns out there's a whole series of mathematical approximations that become available to you when n becomes large. That enables you to do a lot more analytic work than you might ever guess that you can do. And that you're not just relegated to making huge spreadsheets. Okay? Because nobody's going to make a spreadsheet with 10 to 23 columns or rows going down. Okay? But there's this amazing analytic work you can do, all because the number of objects, n, is getting to be very large. And that enables us to just do calculus and algebra. Okay? Pretty much allows us to do statistical mechanics. Otherwise, we really wouldn't be having a class. So that's what we're going to start. We're going to start seeing how we do the deal mathematically with large numbers. isolated system. So we would have to figure out how we think about it if it's not isolated. Okay? For this statement over here to be true, it has to be isolated.
I have a question too.
Oh, well, the fundamental assumption of mechanics is that if it is isolated, and it's come to thermal equilibrium inside, it's isolated from time, then all ion states are equally isolated. We know of no violation of that.